Hello guys, this video is on the open mapping theorem and the boundary inverse theorem. The boundary inverse theorem, it is one of the fundamental theorem of functional analysis. The theorem states let x and y be two Banach spaces over the same field K. For the fundamental theorems, Banach spaces is necessary. And if T be an operator from x to y which is bounded and linear and which is onto, then open mapping theorem states T is an open mapping, and bounded inverse theorem it states hence if T is bijective, then T inverse is continuous, and so T inverse is bounded. So the bounded inverse theorem, it gives a criterion for the boundedness of T inverse, that is for the boundedness of inverse of an operator. Now let's move on to the proof. First let us define open mapping. Simply put, an open mapping is a mapping that maps every open set of its domain to an open set of its codomain. Now first we prove open mapping theorem, which states T is an open mapping. So to prove T is an open mapping, first we need to take an open set in its domain and we need to show its image open in codomain. So let U be an open set in X, then we show TU is open in Y. We have taken the set open in Y because T is onto. So here range set equals to codomain, so TU is open in Y. This is the reason why T is onto was necessary. Now to show TU is open, we take any element Tx of TU, then X belongs to U, but by supposition U is open in X, so there exists a ball Bxr which is subset of U. Now let us decompose this ball Bxr into a ball whose center is 0. So Bxr equals to a ball B centered at 0 plus X, and simplification we get this state. And for the simplicity, for the convenience, we substitute lambda equals to 1 by r and we get this ball centered at 0 radius 1 by lambda is subset of U minus X. We have decomposed this ball into a ball whose center at 0 because we are going to use this lemma. This lemma, it states the image of an open unit ball which is centered at 0, ball centered at 0, then the image it contains an open ball which centered 0 in Y. We are going to use this lemma. Now using this lemma, so we have image of the open unit ball centered at 0 contains an open ball centered at 0 in Y. Then we have this ball, open unit ball, it equals to, we multiply by lambda outside and divide by lambda inside, which is the subset of lambda times U minus X from the relation 1. Now since the open unit ball B01 is subset of lambda U minus X, now we apply mapping T on both sides. T of this ball is subset of this set, and since the image of B01 contains an open ball, the image T lambda U minus X also contains an open ball which is centered at 0 in Y. Now because this set is subset of this set and T of B01 contains an open ball, so T of lambda U minus X also contains an open ball centered at 0 in Y. Now simplification, एउटा सानो करेक्ट गर्नुपर्ने भयो, ल्याम्ला चाहिँ यहाँ मात्र T इज लिनियर एप्लाई गरिसकेपछि ल्याम्ला बाहिर आउने भयो, त्यसपछि Tx लाई उता जोड्दा ल्याम्लालाई डिभाइड गर्दा we get TU contains an open ball which is centered at Tx. This shows TU is open and T is an open mapping. First part of the theorem is proved. Now the second part, which is the boundary inverse theorem, if T is bijective, then T inverse exists from Y to X. Now we have to show T inverse is continuous. To show a mapping continuous, we take an open set in the range and we show that its inverse image is also open. So we take an open set U which is open in X, open in the range of T inverse. U open in X, then its inverse image under T inverse of U, which is TU, which is open in Y. From the above case, this shows T inverse is continuous, because for T inverse, for every open set in its range, its inverse image is also open. Since T inverse is continuous, T inverse is bounded, and hence boundary inverse theorem is proved. Thank you.